talk of today's session. And we have a pleasure of having Sisi Zhou from Caltech telling us about quantum error correction and continuous symmetries.
Hi, can everyone hear me? Okay, so hello everyone. Today I'm going to talk about the trade-off between quantum error correction and continuous symmetries. This is joint work with Zi-Wen from Parameter Institute. So we all know that noise is one of the biggest obstacles in building a real-life quantum computers. And that's why we need quantum error correction, which is an important tool to protect quantum information from quantum noise. So quantum error correction usually works in such a way that a small size logical system is encoded into a large size physical system. So for example, here we have one logical qubit, and it is encoded into this 9 qubit short code. And such type of redundancy could be used to help us correct certain type of noise. So now let's take a closer look at how quantum error correction works. So suppose we have some state psi, and we hope it to stay in its original state in a noisy quantum computer. And one way to do it is through quantum error correction. We could first perform a encoding channel such that any type of correctable noise acting on the large physical Hilbert space could be erased by this decoding channel. So the logical state psi is going to be mapped to its original quantum state after this quantum error correction process. However, this is only how quantum memory works. In real life, we also need to perform logical gates. So here, UL is a non-trivial logical gate that we want to perform in a quantum computer. And in order to do so, we must have a physical gate acting on the large physical Hilbert system, so that the physical gate after the encoding and decoding could be mapped to this logical unitary operation. So from these two diagrams here, we basically see that the structure of the noise must be fundamentally different from the structure of the physical gate. And that is actually the core of the proof of Eastin-Knill Theorem, which basically states that any quantum code that can correct local errors cannot have a universal set of transversal logical gates. So by transversal here, I basically mean that the gates act independently on each subsystem so that noise do not propagate. So it is basically a very nice candidate for fault-tolerant quantum computing. And now let's take a closer look at how the proof works. So we first need something called error correction condition. Suppose we have a noise channel described by this cross operator Ki here. The QEC condition basically is the condition that the noise needs to satisfy in order for it to be correctable. So here it basically says that Ki dagger Kj must act trivially in the code subspace in order for it to be correctable. So then we can see that if the error correcting code can correct all local errors, it means that any local operators E must also act trivially in the code subspace. And now we can take a look at gate operation on the other hand. Here we consider a set of gates which is generated by this H operator here, and we assume H is local, and theta is an arbitrary real number. So this family of gates can only act trivially in the code subspace because any local operator acts trivially in the code. So then we can see that if we consider the entire group of transversal logical gates, the connected component of the identity must act trivially in the code subspace. So, or like it must act as the identity. So with that and some mathematical facts, one can prove that transversal logical gates must not be universal. So actually, inside the proof of Eastin-Knill theorem, one can see that there is a fundamental incompatibility between quantum error correction and continuous symmetries. So here, by quantum error correction, I mean if we have a code such that there exists some recovery channel that can perfectly correct this type of noise. Basically, after the recovery channel, the entire channel is mapped to identity. I say the code is exactly error correcting. And I can say the code is covariant or U1 covariant as long as this representation of U1 gate here, in the physical space, the generator of the representation is HS, and in the logical space, the generator of the U1 representation is HL. So if such type of U1 symmetry exists on the code, I say the code is covariant. And moreover, we know that the code is exactly error correcting as long as this Ki dagger Kj terms act trivially in the code subspace. So then combining these two, we can see that if the physical Hamiltonian HS is a linear combination of the terms Ki dagger Kj, then it must mean that HL must act also trivially in the code subspace, as long as the code is covariant and error correcting simultaneously. And in that case, we don't have a non-trivial U1 covariance on the code. So that basically is a proof of the incompatibility between error correction and continuous symmetries. And this condition here is really called Hamiltonian in crossband condition or HKS condition, and we will assume that to hold throughout this talk. So now we can take a look at the robustness of such incompatibility or the quantitative trade-off between quantum error correction and symmetries. So here we can define the degree of approximate quantum error correction by using some epsilon, which is the distance measure between this error-corrected noise channel and identity. And we could also use delta, which is the distance measure between this physical gate acting after the encoding and this logical gate acting before the encoding. So to be more specific, here we'll use purified distance as our distance measure. And in order to derive epsilon, we need to minimize over all possible recovery channel. That means we have to choose the optimal recovery channel. And there are actually three types of ways to define delta. First one is called global covariance violation. Basically means that we are going to maximize this distance over all possible theta, or we are going to maximize this distance over the entire group. And there could also be like local covariance violation, which will be defined using the derivative of this distance. Or there could be also charge conservation defined using the difference between the charge operators before and after the encoding. And we are only going to focus on the first definition here in our talk. And the discussion on the rest of the two definitions will be included in our paper. So now let's state our main results. First, we derive various trade-off relations between quantum error correction and continuous symmetries. So we are going to focus on these two types of trade-off relations in my talk. Here, delta HL and delta HS basically represents the strength of these Hamiltonians. And J is a function of the noise and a physical Hamiltonian, and it is related to the HKS condition. And F here is also a function of noise and physical Hamiltonian, and it is related to the quantum Fisher information of this quantum channel. So we can see that when epsilon is small, delta is going to be lower bounded by a positive number and vice versa. So basically, it means that the incompatibility between error correction and continuous symmetry is robust. And we will also provide some code example that nearly attains these lower bounds. And I also want to remark here that there are many nice previous work that discuss the incompatibility between error correction and continuous symmetry. But they mostly focus on the situation where the code is exactly covariant. And in fact, if you take delta to be 0 in our trade-off relations, we can recover the previous bounds. Okay, so now let's first take a look at the behavior of our trade-off relations on the different noise model. So the first noise model we consider is called random local noise. So it describes the situation where noise happens independently and randomly on each subsystem. So the noise channel is a convex combination of all this local noise. And in that case, we will have delta HS scales linearly, J also scales linearly, and F is going to scale quadratically. So we can see that for sufficiently small delta, epsilon is going to be lower bounded by the scaling of 1 over n. And for sufficiently small epsilon, delta is going to be lower bounded by 1 over square root of n from the first type of trade-off. And from the second type of trade-off, we get only 1 over n. So basically, we can see that under this random local noise model, the first type of trade-off is going to give us a tighter bound. And we could consider another type of typical noise, which is IID noise. So here, each noise happens independently and identically on each subsystem. That means the noise is going to be a tensor product of all the local noise. So in that situation, the scaling of delta HS and J is not going to change, but the scaling of S is going to decrease to the linear scaling. So in that case, for sufficiently small delta, the bound on epsilon is not going to change by this first type. But the second type of trade-off relation is going to give us a tighter lower bound, which is 1 over square root of n. And on the other hand, if we consider like a small epsilon regime, the lower bound on delta is also not going to change. So the lower bound of delta is always going to be 1 over the square root of n, no matter which type of noise we consider here. Okay, so now we are ready to present our first application, which is a limitation on transversal logical gates. So suppose we have error correcting code that corrects random local errors, or exactly like erasure errors on each subsystem. In that case, from previous slide, we already know that delta is going to be lower bounded by 1 over the square root of n. And moreover, if we assume that the code has a transversal implementation of this rotation of HL operator, and here I assume all the eigenvalues of these operators are integers and they are also bounded. And in the situation where D is very large, we can see that the code must be approximately covariant. So, and in fact, we can prove that the delta times D is going to have at most a linear scaling with respect to n. In that case, D must have a scaling at most n to the power of 3 over 2. So for example, if we are considering like stabilizer code here, this basically means that such type of gate can only implement up to O of log nth level Clifford hierarchy. Okay, so now let's present some examples that nearly saturate our bound. So our first example is N13 quantum Reed-Muller code. So here n is equal to 2 to the power of t minus 1. And for example, if t is equal to 3, we are going to consider this two-dimensional code. And we can write down all the Boolean function with degree 1. And if the first digit is going to be 0, then the last 7 digits will give us logical 0 state. And if the first digit is 1, the last 7 digits is going to give us a logical 1 state. And in fact, for this type of quantum Reed-Muller code, it's possible to prove that this logical rotation of Z could be implemented transversally. And we can see here when T is very large, as in our previous situation, the code is going to be approximately covariant. And in that case, one can calculate the value of delta, which is going to be 2 over the square root of n. And it will matches the scaling of our lower bound, which is 1 over square root of n. And there's only a constant factor difference between the lower bound. Our second example is called modified thermodynamic code. So it is actually a code parameterized by a parameter Q between 0 and 1. When Q is 0, the code is going to be exactly covariant. And when Q is equal to 1, the code is going to be exactly quantum error correcting. So it's a code that interpolates between exact covariance and exact error correcting. So for example, when Q is equal to 0, the code is actually defined using the decay state. So by decay state, I basically mean the symmetric quantum state that has a charge, that has a fixed charge. So, and it can be easily seen that the code is covariant, and it was also well studied before in these literatures. And when Q is equal to 1, one can also prove that the QEC condition is satisfied So the code must be exactly error correcting. So one can compute epsilon and delta in this case. And as before, we see that the scaling of epsilon and delta matches our lower bound. And there's a constant factor difference with the lower bound. Okay, so finally, let's talk a little bit about the proof technique of our trade-off relations. So in order to prove our first type of trade-off relations, I use something called charge fluctuation. So charge fluctuation is defined to be the expectation value of HS on the logical 0 state minus the expectation value of HS on the logical 1 state. So by logical 0 and 1, I basically means the code words corresponding to the largest and smallest eigenvalues of HL. And when epsilon is 0, due to the H-gas condition and the error correcting condition, one can show that HS must act trivially on the code subspace. And that basically means that chi has to be 0. So it is this corner on this axis. And when delta is equal to 0, one can actually show that the physical Hamiltonian is going to be mapped to the logical Hamiltonian with at most a constant shift. And in that situation, one can easily prove that chi is going to be equal to delta HL. So because we have a non-trivial U1 symmetry, delta HL must be positive. So chi is actually an indicator of the incompatibility between error correction and covariance. And in fact, we can lower bound delta by the distance between delta HL and chi. So this inequality can be proven just through the definition of delta. And it is also possible to prove a lower bound on epsilon using the absolute value of chi. And this can be proven using the quantum error correction conditions. So combining these two, we can actually recover our first type of trade-off between epsilon and delta. So in order to prove the second type of trade-off relations, we use a completely different technique called gate implementation error. So by gate implementation error, I'm actually considering the composition of encoding, physical gate, noise, and recovery. So when the code is exactly error correcting and exactly covariant, such a composition of these 4 channels is going to give us a logical rotation with respect to theta. However, since we don't actually have we cannot simultaneously have error correcting code and covariant code, we must compute the distance between this error corrected physical gate and this logical physical gate. So we will call the distance between these two gamma. And then we can actually prove that the sum of epsilon and delta is going to be lower bounded by gamma. So that means a non-trivial lower bound on gamma will give us a non-trade-off relation between epsilon and delta. So this is actually proven using some techniques from quantum metrology, and here F is the Fisher information. And so to summarize, we derive various trade-off relations between quantum error correction and continuous symmetries. And the relations are also shown to be nearly optimal in certain scenarios. And there are also other type of trade-off relations based on different symmetry measures that I don't have time to cover. And also some detailed proof techniques from like fields in metrology and resource theory. And I also presented the results in the application of fault-tolerant quantum computation in terms of this limitation on transversal logical gate. And there are also potential physical applications in quantum gravity and many-body physics, where both symmetry and quantum error correction are an important concept. Okay, so that's all for my talk. Thank you so much for listening.
Thank you, Sisi, for a nice talk. We have a time for a few questions.
Yeah, thank you for the very nice talk. I was wondering if there's any connection between, there's no-go theorems about covariant quantum error correction and the properties of continuous variable error correcting codes, like classical continuous variable error correcting codes. Like, I mean, you get similar, no-go results if you have, let's say classical Gaussian states, and with finite widths. And so I just wondering to what extent these no-go theorems are related to that, or is it totally, because here you are also protecting information about the continuous degree of freedom, for example, rotation around an axis, which is a, continuous variable information, basically. Is there any connection, or this is a totally different, I should think of that as a totally different thing?
Yeah, to be honest, I didn't think about the classical code before, but I do think it's a very interesting point. Yeah, might be interesting to consider. Yeah.
Okay, thank you.
Hi, thanks for the talk. So there were various papers before this one that were showing that if you had this like U1 convariance property, then you had one of these Eastin-Knill type results. You seem to have done something more general, including a statement about a certain class of transversal logical gates, where you had this like 1 over like some integer eigenvalues, right? So I like that you're saying something about the transversal logical gates, because I wasn't completely sure whether the U1 covariance was, I'll just answer my question. So do you think that there are any obstacles to proving that you can't have these transversal logical gates for any spectrum that's inside the Hamiltonian? Because there still seems to be like a little artificial constraint in there that is hard to get rid of.
Yeah, exactly. So basically, the constraint here is like the spectrum of the Hamiltonian has to be integer and also bounded. So actually, if you consider stabilizer code, then the first assumption is naturally satisfied. But the second one about the bounded spectrum is actually hard to satisfy. So it's still a gap from like a arbitrary general transversal gate.
Okay.
Yeah.
If there are no further questions, let's thank Sisi and other speakers of the session.
Recording or live recording. Yeah, I think there the third one is yeah, they saw your live version.